Good evening to everyone who's present here today.
Recording in progress.
I'm Mishni Himansha, the Joint Community Service Director from the Rotaract Club of National School of Business Management. Let me welcome all of y'all to the first episode of the Project Sanvadya, where we present to you the details of all you need to know about vaccines. To start off with today's proceedings, we have our guest speaker, Professor Inoka Kure, the Senior Lecturer in the Department of Microbiology, Faculty of Medicine, University of Colombo. And Tarshini Suryarachi would be the moderator for today's session. Over to you, Tarshini, to continue from here, and hope everyone would have an enthusiastic session. Thank you.
Thank you, Ishini. Good evening, ladies and gentlemen. Welcome to Sanvadya, Stop the Spread Beyond COVID-19. I am Tarshini Suryarachi, an NSBM undergraduate and your moderator for this evening. This is the first episode of Sanvadya, Awareness on COVID-19 Vaccinations. Sanvadya is a project initiated by the Rotaract District Steering Committee of RI District 3220 and hosted by the Rotaract Clubs of University of Colombo, Faculty of Medicine, Marthala, National School of Business Management, and Royal Institute of Colombo. They've all come together to help shed a light on the situation at hand. Hope everyone is safe and well, and I'd like to take this moment to appreciate all the frontline workers, the doctors, the nurses, and the Ministry of Health, and every person who's battling COVID-19 and made the process of vaccination at a record-breaking pace. Our guest today is an extraordinary individual who has graduated from the University of Colombo. She is currently a senior lecturer at the University of Colombo under the Department of Microbiology, Faculty of Medicine. She is an expert microbiologist who's been awarded the Presidential Research Award back in 2002. She has, till today, her researches have been recognized on a global scale. Let me warmly welcome you, this talented individual, Dr. Inoka Kure. Good evening, Dr. Inoka.
Good evening, Tarshini.
Professor, so I'm very much honored to have you in this webinar. And before I drop right into the questions, how is everything? How's your Saturday?
It's fine, thank you. Had a few technical defects, as you know, but we've sorted them out now.
It's all right. So we'll drop right into the questions then. So, Professor, back in the 18th century, cowpox was used to battle smallpox. The word cow translates to vacca. I don't know if I'm pronouncing it right, but it's a Latin word. And later it was called vaccinus, and today we call it vaccine. With that, Professor, could you let us know what is a vaccine and how exactly these vaccines work?
So let me first start by thanking the Rotaract Club and also the President Afraniaz for inviting me to give this interview this afternoon. And I hope you all are, after having a good cup of tea and ready to listen to a few words about vaccination. Vaccination was with smallpox. Smallpox was a devastating infection that killed large numbers of people over many centuries, really. It dates back as far as the ancient Egypt. And it was Edward Jenner who realized that milkmaids never got smallpox, and they had wonderful complexions because they did not have the terrible scars of smallpox. And he worked out that it was because they used to get a very mild infection called cowpox, and that protected them from smallpox. So he didn't take much thought. He decided to inject lesions of cowpox or little serum from the lesion of cowpox into someone. It was a little boy on the farm. And then when the boy was exposed to smallpox, the boy did not get smallpox. So then he realized that the serum from cowpox was protective against smallpox. And as you rightly said, since the Latin name for cow is vacca, this was called vaccination. And we still call we still call it vaccination, even though we are not time. We use many different types of vaccines, but we still call it vaccination. So how does vaccination work? I think we should begin by learning how the body responds to infections. There are many germs that can cause infections in people, ranging from bacteria, viruses, fungi, and various parasites. But the body is able to recognize these germs and mount a unique immune response to each type of these infections. For example, if we have a wound that is infected by a bacteria, the body responds with inflammation and the formation of pus. Let me share my screen and show you what this looks like.
Sure, doctor.
Maybe I should begin by telling you a little bit about the SARS-CoV-2 virus. So coronavirus infectious disease 2019, or COVID-19 as we call it in short, is the pandemic that is affecting us at this current time. And as we know, it's caused by the SARS-CoV-2 virus, that stands for Severe Acute Respiratory Syndrome, coronavirus 2, that belongs to the family of coronaviruses. This SARS-CoV-2 virus is an RNA virus, which has a genome, which is RNA, and which is surrounded by a lipid envelope derived from the cell wall with little proteins stuck in it. And since these proteins look like spikes, we call them the spike proteins. And these are what give this lovely appearance of a crown when you look at it through an electron microscope. And that's how they get their name, coronaviruses. So this coronavirus can enter the body by binding to a particular receptor in the cells of our lungs and other cells. It's called the ACE2 receptor. You can see it here on this little cartoon magnifying glass on the right of your screen. So that is how the virus enters the cells. And like any other virus, it loses its envelope, it loses its proteins, and it's just the viral RNA that gets formed into different proteins that are needed for the virus. And then these proteins come together with new RNA to form new viruses. So that's how a virus infects a person. So as I said, viruses are only one type of infection. There are many other types of infections that infect the body, and the body mounts an immune response. So as I said, for example, so these are the types of immune responses and immune cells and other structures that take part in an immune response. But don't worry about the details. I'll just give you some examples. For example, if a wound is infected by a bacterium, then the body responds, as we all know, with inflammation and the formation of pus. We all know what pus is. Now, pus contains a lot of white blood cells, and namely these little neutrophils that you can see at the bottom left-hand side of your screen. And it's the neutrophils which then will destroy the bacteria and control the infection. So here you are, here's pus in your wound, and the pus consists of these neutrophils which will come in, gobble up the bacteria and control the infection. Now, in addition, a little later, other white blood cells called lymphocytes, which is what we are interested in today, they get activated. And some lymphocytes produce antibodies, and other lymphocytes become T cells. And these antibodies and the T cells act together to clear our infections. Now, the very special feature of these lymphocytes is that they have a property called memory. In other words, they are able to remember the infection. Therefore, if you get infected with the same germ a second time, maybe months, years, even decades later, these lymphocytes are able to remember the infection and then get activated very rapidly and even destroy the germ before it has a chance to set up infection. You can see that here. That is why, for example, we get measles only once in our lifetime, because in the first infection, we generate an immune response, as I said, and then these memory cells are formed. And then the second time we encounter measles, the memory of this measles infection is there within our lymphocytes. And every time we get infected, these lymphocytes act rapidly to actually abort the infection. So we don't get a rash, we don't get fever, we don't even know that this immune response has taken place. We are quite unaware that the immune response has come into play and aborted the infection and, actually cured us before we even knew it. And this immunity is also lifelong most of the time. So what happens in vaccination? What we do essentially with vaccines is we mimic an infection. We mimic an infection. So by using harmless germs or killed germs or parts of a virus or parts of a bacterium, we, as vaccines, we actually trick the immune response. So the immune response imagines that we are having an infection and it responds quickly, similar to having an infection, and we generate those cells I spoke about previously, and then antibodies and T cells, and eventually memory cells that remember the germ. And each time we give a booster of the vaccine. You have heard of vaccine boosters? What we do with boosters of the vaccine is we keep on stimulating the immune response over and over again. Each time we boost the immune response, the memory becomes better and more long-lasting. And it's the same principle with the COVID-19 vaccines. Injection of a vaccine that mimics the virus or the viral proteins leads to an immune response, and the booster dose boosts this immune response to make it more effective and longer lasting.
Thank you, Professor. So I just had a quick flashback of all my biology lessons, to be honest. White blood cells, lymphocytes, whatnot. And Professor, I think we both can agree on this one, that vaccines don't fall from the sky. And there's a whole process to how it actually is made and was chosen. And after a number of trials, only is it distributed to the world. So Professor, I'd like you to share regarding the development of the vaccine, how safety and efficacy is measured, and how safe are these vaccines?
Okay, so vaccines are some of the most safe medical interventions that have ever been invented. Remember, most vaccines are given to children. In the National Immunization Program, all of you have received multiple vaccines and have benefited from vaccination. As we discussed earlier, vaccines have eliminated smallpox from the planet and is poised with the help of your organization, Rotary, to eliminate polio as well. Sri Lanka has an excellent vaccine program and has managed to eliminate infections like measles, congenital rubella, and neonatal tetanus through our immunization program. Now, how are vaccines made so safe? So this safety and efficacy of vaccines are ensured by conducting clinical trials before they are registered for general use. So let me share my screen again. Right, so here you have a sort of an idea of what a clinical trial means. A clinical trial means testing out the vaccine on a selected group of people before it is registered and rolled out into the general population. Now to do this, it's done in phases. So in the first, we have phase 1, 2, and 3. And as you can see, the number of people that are tested, that are guinea pigs in each phase varies. So we first tested on a small number of people on phase 1, that is to mainly look for the dosing and for the safety. Then you move on to phase 2, where again the efficacy is looked at. And then you roll it out in phase 3 trials, where in larger trials, where the safety and efficacy are again monitored. And it is only if the vaccine or the possible vaccine, the vaccine candidate, passes through all these phases and is found acceptable in all 3 phases, that it is registered as a vaccine. Now, it's to do this properly, of course, you use a double-blind process. What does that mean? These trials are done on volunteers, and in the double-blind process, some of the volunteers are given the candidate vaccine. Others, who are called the controls, are given an identical injection, but there is no vaccine. It's some inactive ingredient in that injection. We call that a placebo. So why is it called double-blind? That is because neither the volunteer who's getting the injection nor the doctor giving the injection knows which one is getting the vaccine and which one is getting the placebo. So no one knows except, it's all hidden. Now, these people in the trial are then followed up for a long period of time to measure the rate of infection in each group and also to monitor for any side effects or adverse effects in both groups. And if at the end of a period of time, if you find that the people who received the vaccine have a significantly lower chance of infection than the people who did not get the vaccine, that is the placebo group, then we can conclude mathematically that the vaccine is effective. But as you can imagine, since the rate of any infection in a community is quite low, it will take many years before you can get the required number of infections in each group to make this comparison and do the calculation. So you might wonder how vaccines for COVID-19 were developed so fast. So it's partly because researchers had been working on new types of vaccines for a very long time. And they had developed new sort of platforms. And once SARS-CoV-2 suddenly emerged and the virus genome was now reported in the public domain, they were able to quickly incorporate that information into those platforms and develop these prototype vaccines very quickly. Then, since this was an emergency, they decided to run the 3 phases of the trial, that's phase 1, 2, and 3 in parallel. And so that was another way of ensuring that these trials were conducted very quickly. And of course, we know that since COVID-19 was spreading so rapidly and there was a high infection rate in the community, so the number of infections needed to do the calculations in the infection rate in the vaccine group and the placebo group happened very fast. And it was very, so we could quickly do the calculations and judge whether the vaccine was efficacious or not. However, you may also realize that all the COVID-19 vaccines have been given what we call emergency approval by the WHO. So that is because these phases have been relatively short compared to other vaccines, and therefore there is some kind of caution in their approval. So they call it the vaccines are given emergency approval. Then you asked about safety. Well, the same groups are then also followed in terms of any medical issues that they have during this time. They are followed up, both the vaccine group and the placebo group. Mind you, nobody knows which is the vaccine group, which is the placebo group. They have to all report any mild or severe, anything that happens to them really during this time, whether or not they think it is related to the vaccine or not. And these are investigated. And these adverse events are documented and investigated, and again a calculation is done to see whether there is any relationship with the vaccine, first of all. And after doing that, if we find that the adverse events are mild and temporary and not very significant and the vaccine is very safe, then the vaccine goes on to apply for registration. However, if they find that there are severe adverse events that are common, then of course the vaccine is abandoned. And in fact, even with COVID-19 vaccines, many vaccines were abandoned. I will plug in my battery.
Sure, Professor.
So sorry about that.
No problem. Ready when you are.
So, so as you can imagine, it usually takes years or even decades to develop a safe and effective vaccine. But because of this sort of coming together of scientists, of volunteers, as you can see here, funders, and the registration, and the WHO, of course, giving a lot of impetus, it was done in double quick time, or I would say even faster than that.
Yes. So, Professor, like you said, for any medicine, Professor, that we consume, doctors always let us know and ask us actually if we have any side effects after consuming the medicine. And likewise, even for the vaccinations, it has its own effects. So, Professor, could you let us know what are the side effects and how common are the side effects, especially when it comes to the severe ones?
Okay. So I think yes, there is a lot of fear sometimes, especially about side effects of vaccines, and that has been hindering to some extent the rollout of these vaccines all over the world, including Sri Lanka. But what we have found, I suppose, one thing we do not appreciate perhaps about this rollout of COVID-19 vaccines is one thing, the speed. I just told you about the speed of the rollout of the vaccines. Number two, the efficaciousness of these vaccines, which we'll come to later. They are quite surprisingly in previous vaccines, it has taken a lot of effort to develop vaccines, and very often the efficaciousness is acceptable, but not marvelous. But these vaccines that have come out, there's a lot of they're quite highly efficacious, and that has been almost like a surprise, like a wonderful serendipitous surprise, that these vaccines have proved so good. And the third thing is the safety. They have been found now. They remember, more than other vaccines, these vaccines, I think, probably the largest number of people in the shortest space of time have been given these COVID-19 vaccines, and such a variety of vaccines. And yet, in the main, the side effects have been really quite mild. I'm sure everyone listening in here today, I don't know whether you are, or maybe you are, this age group is under the vaccine recommended age group at the moment, but you must all know of family members who have received the vaccines. And in most cases, side effects of the vaccines have been very mild and very short-lived. Side effects like pain at the injection site or some fever that lasts for 24 to 48 hours. So, almost 1 billion people have received the vaccines over the world, and in the majority of cases, the side effects have been extremely mild. However, that is not to say there have not been any severe side effects. Like any vaccine, allergy can be a problem, usually not to the vaccine itself, but to the other components that are included in a vaccine. And there certainly have been instances of allergy, and leading sometimes even to death. It's hard to talk about side effects of COVID vaccines in general, because of course, there are many different types of vaccine out there. That's another fortunate thing, that we were not, hostage to a single vaccine, but we had this choice, almost a smorgasbord, some people call it, the buffet of vaccines that are available at different prices, different kinds. And of course, each one has its own safety profile. So the one that we rolled out first here, that is the Astrazeneca vaccine, you may have heard that in certain young people, very rarely, of course, it led to some kind of clotting problem, which sometimes even ended fatally. So in some countries, they have decided not to give the Astrazeneca Covishield vaccine to people under younger people, and they're restricting it to the over 60s. So like that, there have been sort of severe side effects attributed to particular vaccines, but in general, these are extremely rare. Though they get a lot of publicity, they're extremely rare. I know it's still the thing about vaccines is you don't have to take it, right? It is not like something you have to take for ischemic heart disease or something like that. It is something almost voluntary. So because of that, it's imperative that they should be safer than any other type of drug. I mean, you can tolerate side effects in drugs that you take for blood pressure treatment or even antibiotics because they are life-saving at that moment. But a vaccine is a preventative. At that moment, you are healthy, you are well, and this is going to prevent something in the future. So in that type of situation, safety is absolutely imperative. So, but I think the vaccines that have rolled out to a large extent do sort of pass the test of safety when you sort of think of quickly they were developed. Again, we should be surprised how safe they really are.
And with that, doctor, regardless of being vaccinated or not, we are always told to avoid like certain activities or stay isolated, wear the mask and more. And all of this is to actually shield ourselves from the virus and avoid further transmission. So, Professor, after being vaccinated, how protected are you and I from this COVID-19?
Okay, so the first trials that we talked about, remember we talked about clinical trials.
Yes.
Now, and how they judge not just safety, but efficacy. So that's what you're asking me. So the first clinical trials, when they look at efficacy, you have to decide what you mean. What is it efficacious against? So those first clinical trials, really, they measured whether the vaccine was able to prevent serious disease and death. So that is what they looked at, the end point or the measurement at the end between the vaccinated group and the placebo group. The end point that they looked at, the outcome they measured was whether the vaccine was able to prevent severe disease and death. And we should be quite happy to know that all the vaccines that have been registered by the WHO so far have really passed the test. I mean, their efficacies vary widely from about 50% to about 98% in preventing symptomatic infection. But those first trials showed that across the board, they were almost completely successful at preventing severe disease and death. So that is what you must remember, that these vaccines do not guarantee that you will not get infected. That was not the endpoint that was being measured. What was being measured is that whether you would suffer symptomatic and severe disease and death. And all the vaccines that have been rolled out now can sort of show an efficacy in preventing severe disease and death. Remember, it is still not 100%. There is nothing out there that is 100%, but it's very close to that in terms of preventing death. Of course, once the trials are over, now it was the trials that showed very, very high efficacy and prevention of death was almost 100% in the trials. When you roll it out in the whole population and you get billions, obviously these efficacy rates drop slightly because you're in real world conditions. However, we can be confident that all the WHO registered vaccines are able to protect the vaccine need to some degree. But you must remember two things. First, this efficacy is true only 2 to 3 weeks after getting your second dose. So that's the first thing to remember, that until and if you get your second dose and wait maybe 2 to 3 weeks after the second dose, that's when this efficacy that kicks in. And also remember, the efficacy is not 100% even at that point. Therefore, we should not be surprised if people who have received both doses of any vaccine get and have completed their 2 to 3 weeks after the second dose, still get what we call breakthrough infections. Why? Because no vaccine is 100%. So say the vaccine is even 98%, you will expect 2% of breakthrough infections. And some of the vaccines are only about 50% to 67% effective. So there will be much more breakthrough infections in people vaccinated with those vaccines. But thankfully, these breakthrough vaccines are usually very mild in nature. Now, the original trials did not test whether the vaccine could completely prevent transmission. So trials to measure this efficacy to prevent transmission are actually ongoing now because, of course, the vaccines are being rolled out and you can now measure their ability to interrupt community transmission. So we should have the data very soon. I think the preliminary data does show that similar to the way it prevents severe disease, there is some effect on interrupting community transmission. But obviously, this is going to be much, much less than the efficacy to prevent severe disease. So if your efficacy to prevent severe disease was 67%, it's going to be much less regarding efficacy to prevent transmission. So remember, the efficacy to prevent transmission is going to be quite low, and therefore, even people who have had both doses of the vaccine and after 2 to 3 weeks later, you still have to practice all the COVID-19 precautions that we know of restricting movement, avoiding crowded places, social distancing when you are with others, washing hands with soap and water frequently, wearing a mask, and practicing respiratory hygiene. So that does not change whether or not you're vaccinated. Remember, we also do not know how long the immunity generated by the 2 doses of vaccine will last. It's only been 1 year since the first vaccines were used. So far, it seems that the immunity is long lasting, but some countries have actually started giving, as you know, a 3rd dose of vaccine in very vulnerable populations to boost immunity. So that's a space to watch. We'll have to watch and see how long this immunity, which is already incomplete, how long it will last.
Thank you, Professor. And like you said, I think that's a misunderstanding among us that once you are vaccinated, actually, you're completely recovered. You won't get COVID. That's not the case. And thank you for clarifying that, Professor. So with that, I think there's around 15 vaccinations listed according to the World Health Organization, and some of which are yet to be approved by the WHO. And about 5 types of vaccines are released to Sri Lanka, if I'm not mistaken. And Professor, could you let me know as to what are the types of vaccines and how different are they?
Yes. To do that, let me share my screen because a picture is worth 1,000 words, I think.
Sure, go ahead.
Okay, so in this rather nice slide that I got off the internet, can you see it properly? Yes, here we are. It's a very nice cartoon of the types of approaches that one can have about making a vaccine, manufacturing a vaccine. So what can we do? We could take a virus and inactivate it. So you can take a virus, you grow it in cell culture, you kill it. And so once you killed or inactivated the virus, it is no longer harmless, but it is still perfectly able to generate an immune response. So that's how the Cynopharm and the Sinovac vaccines that you've heard of were made. Basically, SARS-CoV-2 virus from patients were grown in cells in the laboratory, and then these viruses were killed and used to make these vaccines. So these vaccines contain dead virus. It's also possible to grow a virus in cell culture, and once you grow it over and over again, it becomes less and less dangerous. So what you do is you create a weakened or attenuated form of the virus. Like is done in measles virus, is an attenuated form of the measles. The measles vaccine is an attenuated form of the measles virus. But at the moment there are no COVID-19 vaccines that are live attenuated at the moment. However, you don't really have to inject the whole virus to get an effective immune response. You don't have to inject, inactivated virus or attenuated virus to get an immune response. Remember, I told you that it's a spike protein on the surface of the viral envelope that binds to our cells. So theoretically, we know that if we generate a good immune response to the spike protein alone, that should be enough to protect us from infection, because it will bind to that spike protein, and the immune response will attack the spike protein and prevent the spike protein from binding to our cells and abort the infection. Right. So now the target of our vaccines was now the spike protein, to generate immunity to the spike protein of the virus. Now the next question is, how can you generate enough spike protein in your body so that you stimulate an immune response to the spike protein? So to understand how scientists address this challenge, you must know a little bit about how proteins are made in a cell. As you know, DNA genes in the nucleus, they contain information or coding for all the proteins. And this coding is copied into a strand of messenger RNA or mRNA, okay? And this mRNA can now move from the nucleus into the cytoplasm, and it's used as a template to make protein. So using this knowledge of how protein is synthesized, that is, DNA is copied into mRNA, and it's the mRNA that moves into the cytoplasm and is translated into proteins, scientists used innovative methods now to generate spike proteins in our body. One method was to make a vaccine that simply consisted of a large number of copies of that mRNA template for the protein. So once this mRNA vaccine, right, large numbers of mRNA template is injected into the body, the cell is able to take up this mRNA and use this coded mRNA to make, again, large amounts of spike protein and generate an immune response. So this was the way that the path that Pfizer Biotech and Moderna went. They decided to make mRNA vaccines. They were already working on mRNA vaccines, and they used it when SARS-CoV-2 came along. They used the same technology to generate spike protein mRNA, and that is what is in their vaccine. The spike protein mRNA is injected into the person, and then it starts making spike protein, because that is what mRNA does. And we generate immune response to spike protein. And as we can see, these are some of the most effective vaccines that are available for COVID-19. The only problem is this RNA is extremely temperature sensitive. And so these vaccines have to be stored at very low temperatures, like -70 or -80, which is difficult to do in our low resource settings. You need these huge freezers, -70 or -80 freezers. Now, another way you can a vector means a carrier. It's a carrier virus. It carries the spike protein gene in the vaccine. So basically, that vaccine is that has been spiked or carrying this viral vector into the person. Those genes are expressed, and they start producing this spike protein again, and then we so this virus is genetically engineered, you can say, to keep on producing the spike protein, and therefore we generate the spike protein is sent into the body, and we generate an immune response. So luckily, scientists had already identified such harmless viral vectors, mainly adenoviruses. They were already ready and waiting in the lab. So all they had to do was cut out the correct gene, put it into the viral vector, and they had the vaccines. So Astrazeneca vaccine, including the Covishield and the Sputnik vaccine are examples of this technique of a viral vector. There are also vaccines that are just made of purified proteins, just spike protein taken, concentrated and purified, vaccines like Novavax, but we have not used these vaccines in Sri Lanka as yet. So we should really be grateful to scientists all over the world who are ready and waiting, really, with the technology and the knowledge and the attitude and the competence to create these vaccines and make them available, I think, in a record time. And also to the companies and other, manufacturing like Serum Institute India that were ready to roll them out in huge numbers, counting billions of doses. However, since these vaccines are different others, so at the moment, it seems that the two mRNA vaccines, Pfizer and Moderna, are the most effective, with efficacies approaching 95 to 98%. The viral vector vaccines come next with efficacies of 65 to 75%, whereas the inactivated vaccines have efficacies that are closer to 50%. However, these efficacies are all quite good when you think about vaccines in general, and we can be confident that these vaccines are able to protect us from infection to varying degrees. But most importantly, all of them will reduce your likelihood of dying from COVID-19. So remember that even people who do not die from the infection take a long time to get back to work and to normal life. And we are now hearing of a syndrome called long COVID. I don't know if you have heard of that syndrome. It's called long COVID, where people who seem to have recovered from infection still complain after many weeks, months, and years of having symptoms and tiredness and fatigue, and sometimes even more and confusion, and many other symptoms that still have not left them, even though it's been many months since their infection. So we think that vaccination will also not only prevent death, not only prevent severe infection, but also prevent this long COVID complication.
I was not aware of that, Professor. Thank you for letting us know. And Professor, there's one more question. Before I get into the next question, actually, this is for the audience to know. And Professor, please do correct me if I'm wrong. When we are speaking of variants are new mutations or changes in the virus, making it more dangerous or contagious in the case of COVID-19. So, Professor, could you let us know as to what is the effect of the variants on these vaccines?
Okay, so these efficacies and trials and clinical trials and all that I quoted the numbers were really, these studies were done when it was the original virus from Wuhan, the Wuhan virus that was circulating in the world. Since then, 2 years on, the virus has mutated hundreds and hundreds of times and really generated hundreds of variants. I don't know if you're aware of that. It's not just a few variants. It's an RNA virus. It mutates continuously and generates hundreds of variants. But among this large number of variants, there are few variants that we call variants of concern. That means they make us worry. So why are we concerned or worried about these variants? This is either because they are more transmissible or because they cause more serious infection. For example, the Alpha variant, which was first described in the UK, was a highly transmissible variant. It spread rapidly throughout the world, replacing the original virus completely. Now we are faced, as you know, with the Delta variant, which seems to be even more transmissible than the Alpha variant, and very rapidly replacing the Alpha variant wherever it was prevalent. There's also increasing concern that this Delta variant may also cause more serious disease, but that is still not completely, it's still being studied. It's still not very certain. There's, yes, it's still, the numbers are not out there yet, and it is still not clear whether it is more serious or not. But there is a concern that it may cause more serious disease than the Alpha variant. And then your question, there's also a concern that the immune responses generated to the vaccine viruses, that remember, these vaccines were made using the original wild Wuhan virus and the genes of the original wild Wuhan virus. So there's a worry that these vaccines may not be as effective against the newer variants like Alpha and Delta. So what is the real world data? There is actually a paper, I think, that is published this week that talked about it. And they did find that there was some degree of loss of efficacy against the Delta variant. They studied particularly the Moderna vaccine, and they studied the Astrazeneca vaccine. And for a single dose, the difference in efficacy was quite significant. But when you took the 2 doses together and you have been fully vaccinated, the fall in efficacy was not that much. So there is definitely a fall in efficacy. I think that is certain. The efficacy of the vaccine, the original vaccine against the Delta variants, as opposed to the original virus, there is a fall in efficacy. We are sure of that, but it seems to be fairly modest, and I don't. It will not make a huge impact at the moment, but certainly there may be variants out there that are on their way. That are on the way, and then this this may change. So it's certainly something we have to worry about. And I think the most important thing we have to realize is, okay, why do these virus variants develop? It's important to know that the virus variants can only develop if there's rampant transmission and circulation of the virus in the community. If the virus spread is controlled, then the number of mutations that are happening are going to be less. So an important effect of increased vaccine uptake in the world is to reduce this virus circulation, this rampant viral replication, and reduce the formation of new and dangerous virus variants. So I think the emergence of these viral variants that compromise transmission, compromise, the danger of the disease, and compromise vaccine efficacy. Again, one solution to that is wider vaccination, and to control the transmission and spread and replication of these viruses, so that less mutations are likely to happen.
Thank you, Professor. And Professor, there are a few questions that were given by the Google form. We sent out a Google form to the participants, and they have a few questions. These are coming from the participants themselves. So one of them is, why is Cynopharm rejected in some other countries?
I don't know whether it's actually, you mean the people who have taken the vaccine are not allowed to travel to other countries? Is that what maybe that's what they're asking?
Maybe.
Well, it all depended, I suppose, on which vaccines you chose at the beginning. Right at the beginning, there was a smorgasbord, as I said, of vaccines. And of course, the Americans would choose the American vaccine. So they went for Moderna and Pfizer almost exclusively. And the UK went, of course, for the Astrazeneca. And then Europe went for a mixture of both lots. So in general, those first world countries, Canada and others, very early in the piece, almost before these vaccines were manufactured, they had already ordered the doses. I wonder if you realize that. Most of these vaccines were ordered before they were even tested, before the clinical trials. While the clinical trials were ongoing, these vaccines were ordered and paid for ahead of time. So that was one of the things that happened. That is why those countries which had the resources, they could already order ahead of time. Even if it didn't work, they had already paid up. And they were lucky enough to get the first, millions of doses to their country. Sometimes they even ordered many times more than the actual population, probably because they didn't know whether these vaccines would work. So they would order, 2 different types of vaccines, enough for the whole population. They had the resources to do that. So everybody else came far, behind, far second. So. Maybe it's the lack, there is a lack perhaps of, there's a lack of knowledge perhaps in those countries about other vaccines, and lack of experience about other vaccines. As you know, everyone's closed their borders in any case, because they do not want these variants and being brought in, and unknown variants may come in. So anyway, these borders are closed. So I guess you stick to what you actually know, where you are confident, where you have the knowledge and the experience. So that may be why the countries which have no experience, say in Sinopharm, would not accept Sinopharm. But on the other hand, the WHO, which takes a much more global view and has a much more broad perspective, and is in touch with many more countries from the whole spectrum, from the first world to the third world, they have a broader viewpoint. So they view the documents and the data from all the vaccines, and based on that they make their recommendations. You have the pre-qualified vaccines, as we call in WHO. Remember, again, these are all emergency. Every one of them is an emergency, for emergency use only, and they will accept what they feel is an acceptable vaccine that will be efficacious to sort of interrupt this dreadful pandemic. So they are, so they have perhaps more experience. They have people who have, who are experienced in all these vaccines. So they take a broad outlook. So I think that may be the reason why some countries take a very narrow view of what is acceptable, and some countries take a much of a broader and liberal view to vaccination.
Thank you, Professor. And there's another one over here that they want to know if in Sri Lanka, can above age 18 can get vaccinated?
Yes, I think now the whole point of vaccines should be rolled out in a methodical manner, because we must have a goal of our vaccination, and then your vaccine policy should mirror that goal. For a vaccine to come out, there must be effective vaccines, no doubt. You must also have a public health infrastructure so able to deliver vaccines in a proper manner, and Sri Lanka is very good at that, as you know. Then you must also have a vaccine policy. So we have been a little bit not quite firm in our vaccine policy, but in most countries, or what WHO recommended is that we go first, we vaccinate those who are most vulnerable or in danger. So those are the elderly above 60, and of course, those with comorbidities. Once that cohort is over, then you move down gradually, 50 to 60, 40 to 50, and so on. So at the moment, with this huge rollout that we've seen last week, we seem to be covering the elderly age group, and then we're moving down. And certainly, I think this week we have the call has gone out that we can now go down below 30 to the younger persons. So starting with the 18 to 30 age group, and then moving on even to children. So definitely that will happen. In the US, already they have vaccinated all the eligible adults who came forward for vaccination, and they have already started childhood vaccination in the US.
Thank you, Professor. Professor, there's one more question over here that they want to know what's the difference between Cynopharm and Moderna, the two types of vaccines.
Cynopharm and Moderna.
Moderna, yeah.
Okay, so Moderna is, as I said, an RNA vaccine. It has got messenger RNA in it. That is the code for the spike protein. So basically, it's packaged RNA, packaged in some lipid or something. And because it's RNA and extremely fragile, it has to be kept at -70 or -80. It has very complicated packaging, and it has to be stored in these -80 to 70 freezers, and they can only be taken out just before vaccination. So transporting it here and there can be an issue. So Moderna similar to Pfizer. They both have extremely high efficacious rates of nearly 98% or something. Which so they seem to be the vaccines that seem to have given the highest efficacy in the world. Then Sinopharm, as I told you earlier, is a killed vaccine. So here the virus is grown in cell culture into large amounts of virus and then killed and inactivated. So you are injecting a whole virus there. So you generate immune response to the whole virus. So maybe because it isn't, a purified, a single protein that you're giving, maybe because of that, you would generate a wider, broader immune response, but perhaps one that is not so great against spike protein. It will have a wider range of antibodies against all kinds of proteins of the virus because the whole virus is there, but maybe not so high against the spike protein per se. So therefore, its efficacy is much lower. But certainly, it has been shown in the trials and registered by WHO because it is efficacious. Perhaps not as efficacious as Moderna, but certainly efficacious. And of course, the advantage is it can be stored in a fridge anywhere in the country and transported anywhere. And so it's very easy to administer in our setting. You don't need any special freezers to store your Sinopharm.
Thank you, Professor. I hope that answered the question. And Professor, this one I also want to know personally myself. This was asked from the participants. What's the most favorable vaccine in your opinion?
I'll just quote WHO. The most favorable vaccine is the vaccine closest to you, the vaccine that you can get. If you can get a vaccine today, just take it.
Thank you, doctor. I hope that answered everyone who was curious as well. And before I get into the last question, I'd like all the audience to know, participants, please fill out the Google form that has been put on the chat. And thank you. Last question, Professor. This one is, yes, okay. So is there a fair distribution of vaccines globally and locally, in your opinion?
Right, difficult question. But anyway, anyone who's been watching the WHO speeches on the news or anything will know that one of the main themes that WHO is harping on is about the inequitable distribution of vaccines. As I told you earlier, as soon as the vaccines became, just a twinkle in a scientist's eye, the richer countries had booked enough vaccines to vaccinate their populations multiple times, right? Probably because they were not sure which vaccine would probably be found to be effective. But of course, in response, the WHO set up the COVAX facility, as you know, to ensure that even the less wealthy countries would get at least a proportion of the vaccines they're going to need for their populations. So certainly we too have benefited from the COVAX facility, as many other countries have. And of course, these COVAX vaccines do come from the richer countries. They donate part of their stocks to this COVAX facility. So that was one thing that I think a great initiative by WHO. But it took a long time to roll out because people were, too busy vaccinating their populations to really pay much attention to it till maybe this year. However, as I told you, the first world countries have actually finished vaccinating their eligible adult populations. They're moving on to vaccinate children. But in many countries, they've barely started, adult vaccination. And there's a huge lag between certain countries. So remember, it may not only be due to vaccine availability. I told you that you need a good public health network and you need trained health personnel to administer vaccines. Whether they are donated or bought, they have to be given, stored and given. So in that regard, of course, as I said, Sri Lanka already had that excellent public health network. That is it's an example to the world. But in other countries, that network may need to be set up before they can even think of starting, rolling out the vaccine. In huge countries with sparse populations, it's always going to be a lot more difficult. Sri Lanka is a small country with a, dense population. Then also, I said you must have a vaccine policy also. And then the public also must cooperate. There must be sort of a demand for the vaccine. And again, in Sri Lanka, we have an educated population with the literate population. And you see the queues outside the vaccine centers, and that shows, the huge acceptance that Sri Lankans have for vaccination. That may not be the same everywhere in the world. So it's not just sufficient to have the vaccines. You must have infrastructure, public trust in vaccinations and in the healthcare system and in the government, and consistent policies in vaccination, and then we will be able to do that. So that's what you need if you really want vaccine equity. There's a lots that have to be done, but we hope at the end of this pandemic crisis, we will have a lot more equity.
Thank you, Professor. I know I did tell you last question, but our audience is very curious. So here's one last one. This is from the audience. Is it causing any excess blood coagulation in the future?
The vaccine, well, in the future, right now, the long-term effects of vaccination, I don't know whether that's what the person is asking. I don't quite understand the question. In the short term, Astrazeneca, as I said, there have been rare causes of blood clotting, even leading to death sometimes in the younger persons. So that has been noted, though it's extremely uncommon. It is noted with both types of adenovirus vector vaccines, both the Sputnik and the AstraZeneca. But if you're asking about long-term effects, in the long term, whether vaccination will have effect on blood coagulation, I don't know. No one knows that. It seems to be very unlikely. If you think about all the, many vaccines that we are giving our children, we have never heard of any vaccine that has a long-term side effect that, comes up after 5, 10, 15, 20 years. We've never heard of such a thing happening with any kind of vaccine that we know to date. So that does not say that it cannot happen, but most vaccine side effects really happen in the first year or less, maybe few months after vaccination. It's very unlikely that there will be a very long, drawn out effect of vaccination. On the contrary, the infection is now very well known to show some long-term complications that can persist and maybe become even lifelong: cognitive, neurological, psychological, and even fatigue. New syndromes have been, I told you, that have been incorporated under long COVID, have definitely been shown to happen. So we do know that infection causes long-term complications, but we don't know it for the vaccine. I would think it's unlikely, but I cannot be sure.
Yes, Professor. Thank you so much for answering that. Audience, I hope you are, all the questions have been answered. And before I close it, actually, I'd like to call our project organizer, Ishini, to give her thank you speech. Ishini, the stage is yours.
Yeah, thank you. So I'd like to take this moment to thank our guest speaker, Professor Inoka, for giving us a very insightful session about vaccines. Thank you for sparing your valuable time for us today, Professor. And I'd like to thank our moderator, Tarshini Suryarachi, for a job well done and for keeping the momentum of the session throughout. And also to all the host clubs with the district steering committee in making this session a success. And also, I'd like to thank the audience on behalf of the organizing committee of Stop the Spread for being here with us today. And I hope to see you all in the upcoming sessions of this project Stop the Spread as well. Thank you. And Tarshini, would you like to add something?
Yes, please, I do. Professor, before I give my thank you speech, I'd like you to give a few words. Do you have anything you want to share?
Well, only that what happens next, like what's in the future for all of us. It's such an uncertain time, isn't it? It's like living in a movie or something like that. You suddenly wake up and you're in this movie. You're an unwilling participant taking part in this. You have not written the script and we have no idea what the script is going to end with. So some people feel that coronavirus, SARS-CoV-2 is here to stay. But you can think of it like a flu virus. The flu virus has been here with us for 100 odd years, and it is there. It causes infection every year, and vulnerable people need to be vaccinated before, every year with a booster to prevent influenza. So we might end up with SARS-CoV-2 joining influenza as a background virus, something like dengue or something that is there all the time. That is dangerous to certain people, and where we will need to get a booster dose of vaccine once a year just to keep our immunity up against the variants that come up. So it might just melt into the background in the future. We'll have to wait and see.
Thank you, Professor. And before I close this, thank you so much, Ishini, and thank you, Rotaract Club. And Professor, once again, thank you so much, Professor Inoka, for spending your valuable time here with us today. With that, my dear audience, thank you to you, and have a great day. Stay safe and take care.
Thank you.
Participants, you may leave now. Thank you so much.